You're listening to the FQxI Podcast. Today,
But are they really paradigm shifts?
why aren't fundamental science and technology more disruptive?
If you think back to when we were all children or our parents were children, we expected to have things like flying cars and stuff like that now, and we don't have that.
Physicists Ian Durham and David Sloan join the debate.
Junior scientists, people getting into, for example, their first tenure track position, even all the way through the chain, are being pushed to publish and to publish rapidly. And so there's a very strong discouragement away from doing this truly original, risky research.
As FQxI launches its new $40,000 essay contest.
And in fact, how could science be different today? So are there things that we do today? Are there institutions? Are there methodologies that we are using in science that could be improved upon? And if we had to rebuild the system from the ground up today, how would we do it?
I'm Zeeya Merali. Welcome to the podcast from the Foundational Questions Institute. You may be expecting the next episode of our Great Mysteries of Physics series, which, this week, will be tackling the topic of fine-tuning and asking just why the fundamental constants of physical reality seem so very well suited to allow the evolution of life. That episode will be dropping soon. But first, we're taking a bit of a detour and thinking about how science itself is done. If you have visited our website, FQxI.org, recently, you will have noticed that FQxI has had a bit of a makeover. Right, that includes a new home for the podcast page, qspace.fqxi.org/podcasts. That's the letter Q followed by the word space, qspace.fqxi.org/podcasts. It's going to take me some time to get used to. I'll keep repeating it. I hopefully won't get it wrong. But never fear. We are the same old familiar podcast, and to prove it, we even have Ian Durham, FQxI member and quantum physicist at St Anselm College in New Hampshire, back with us. Hello, Ian.
Hello, everybody.
And to add to the excitement, we've also got Dave Sloan, FQxI's Scientific Programs Director, who's been highly involved in redesigning the FQxI website. So if you don't like it, please contact him. And who is also a physicist at Lancaster University in the UK. Hello, Dave.
Hi, everybody. Hi, Zeeya.
You sound so pleased to be here, Dave.
Well, given that you've just directed everything that people find wrong with the new website to me, yeah, that's going to be fun to deal with. Thank you for that. I will say it has been a lot of hard work by the whole team to get this working. We're quite proud of what we've done, but there are no doubt still a few bugs in there, so if you do find them, please do let us know.
Yes. Sorry, we should all take partial blame for that. So, yeah, you can contact any of us at podcast@fqxi.org. So why have we all gathered here? Well, there are a couple of announcements about new FQxI opportunities that we want to share with you. And then we're going to get into discussing a new paper that came out earlier this year in Nature about an alleged fundamental shift in science and technology. The alleged claim, or the claim being, that papers and patents are becoming less disruptive. We will come to that shortly. But first, the two opportunities, one of which is not entirely unrelated to the topic of the podcast today. The first being a new masterclass that we will be running on the nature of time in the summer with Ian Durham, which some of you may have already heard about. And the second being the announcement of FQxI's new $40,000 essay competition. Right, so over to you, Ian, to give us another little ad for our podcast listeners about your masterclass on the nature of time.
Thanks. This is really going to be an interesting experiment, an interesting opportunity. I want to emphasize that this class is meant for anyone. And so in this class, we're going to be looking at time, going back to really fundamental stuff and how we perceive time, how other animals perceive time, what time is. what actually is it? There's some really interesting questions about that. And we're also going to talk about clocks and what clocks are. What I really want people to take out of this, regardless of where you come from, is I want you to think differently about not just time, but about the world and how things work.
This is a class that is going to make you think differently about the world regardless of who you are. I hope to get a whole variety of different people to take this class. So I don't want scientists to think that this is not for them, but I also I don't want the general public to think that this is not for them either. As someone who actually is a mathematician as well as a quantum physicist, I have a tendency to think of things from a first principles way. I'm going to question everything down to the nature of numbers. So I think you want to think deeply about something, regardless of who you are. This is the class for you.
And I should just mention, by the way, since this is an ad for FQxI, that this entire class, it's been like 10 years in the making, and it was inspired by an FQxI conference in 2011 that was on the nature of time. That conference basically prompted me to completely rethink everything I thought about time and what time really meant. And over the course of the years, I just have really built up this different way of thinking about it, and I developed it into a course at my college, and now we're going to turn it into the master class. So I'm hoping everybody joins us for that, and I'll pass it back to you.
Yeah, and don't be put off by the fact that he then went on and introduced himself as a mathematician after saying that this is open to anyone. It is open to anyone. He's not going to make everybody do lots of maths, unless you really want to, which you may do. I know some of our listeners very much do want to do so, but he will not force maths upon you. We haven't got the full details of Ian's course yet, but you can register your interest by emailing me or us at podcast@fqxi.org. And you can also subscribe to our general mailing list on the site, fqxi.org, by scrolling down to the bottom of the page and subscribing to our newsletter there. And you will be amongst the first to hear about it when we put out more information about how to register for Ian's course. Basically, I'm just trying to get you to look at our new website, fqxi.org, because we also have information on the new website about the new essay competition. So, Dave, please talk to us a little bit, and I say only a little bit because we will be coming back to it, I can tell. And Dave can talk for a very long time about things he feels passionately about, but give us a brief introduction to the topic of the essay competition.
This year's essay competition is on how science could have emerged differently. So how could science be different, and how should science be different? So there are a lot of ways in which science is constructed. It was constructed historically, in arising, for example, out of natural philosophy, leading from a basis of mathematics into physics, and physics thus reinforcing mathematics as it developed. But you can imagine that this science could have evolved very differently. Historically, for example, biology could have taken great leaps. There's no reason for penicillin not to have been developed before calculus, as an example. So we'd like people to look at how could science have emerged differently, and in fact, how could science be different today? So are there things that we do today, are there institutions, are there methodologies that we are using in science that could be improved upon? And if we had to rebuild the system from the ground up today, how would we do it? Would we have universities? Would we have research centres? Would we have research papers? And can you think of ways in which this could have been done better?
And so one thing that we're trying to do better, so we've been running these for, I don't know, a decade now or more, but this is the first time it's going to be anonymous. So Dave, can you tell us a little bit more about that choice? Why have we decided to do that now?
One of the great things that I've always loved about the FQxI competitions is that anyone can enter. And absolutely everyone can sort of throw their ideas out there and have them up against Nobel Prize winners. So it doesn't matter what your background is, it doesn't matter who you are, your ideas should stand on their own. So we're really doubling down and committing to that on making things anonymous. In this, no one will know who you are, no one will know who wrote which essay. So we have had essays from Nobel Prize winners, and we have had essays from high school students, and each of these can and will win prizes in an FQxI competition. So anonymity puts everyone on a very level playing field. And so the ideas themselves should be what drive forward these essays and what select out of them which are the best.
And so, you know, Ian Durham has won a prize on numerous essay competitions or contests as they were known previously. It will be interesting to see if he enters anonymously this year and how he does, because I know he has a private little competition going with some of the other regular entrants to see who will do better. So this could be fun. But we will be coming back to the essay competition and the topic in a bit more detail later. I will just say now that we are also open to entries that could be in the form of fiction. The topic lends itself very well to thinking about sort of alternate histories and alternate realities, or imagining a new way of doing science. But we're also interested in, you know, actual ideas of how to make scientific institutions better, journals better, the publishing industry better. This sort of brings us on to the discussion of today's podcast, which was suggested by Ian Durham after a paper came out in Nature by Michael Park, Erin Lehigh, and Russell J. Funk, which I know multiple people on this podcast think is an excellent name for a scientist. Ian, you picked this paper up and wanted to chat about it on the podcast. Why?
So the basic premise of the paper is that scientific disruptiveness has gone down in the past, 40, 50 years. And I think I was on my way to work, and I was, somebody had mentioned this, and I was thinking about it in relation specifically to our annual countdown. And I was thinking about whether it was true, because this is a topic I've thought about a lot. I think it's particularly relevant to FQxI's whole mission, is disruptiveness in science declining?
So, Ian, can you bring this to life a bit and explain why the world needs more disruptive thinking?
When I was a kid, my parents are not science people. I thought I was going to be a theater major in college. But the thing was, I got into science, and what drives me is the fact that I never grew out of the why stage as a kid. So if you've got kids, they ask, why? Why, Daddy? Why? And, they keep asking. And eventually you say, well, just because. I never got out of that stage. I constantly want to know why. And one of the things I've come to realize is that science is an extremely creative field. And in being creative, you have to be willing to accept failure. The idea that sort of comes to me in analogy is in music. So some of the people that I've been listening to recently, there's a band called Bauhaus. What Bauhaus did, and what very early Pink Floyd did, so before they became famous, is they often just tried stuff, random stuff. And sometimes it worked, and sometimes it didn't. But boy, when it worked, it was amazing. And it was transformative in the sense that they ended up inspiring a huge amount of other stuff later on that is sort of more mainstream, but wouldn't have happened had it not been for some of these things. And the Beatles are another example. They did some crazy stuff. They pioneered things. And I think that is really key to the FQxI mission, right? So I want to just give then some examples of when disruptive thinking have really made a big difference. I'm a quantum guy, and I do a lot of quantum information work. And quantum information is sort of the prototypical field where quantum computing is huge now. There's a tremendous amount of money invested worldwide now in all things quantum, because largely of this quantum information or quantum computation revolution, sometimes called quantum 2.0, people are calling it. None of that would have happened if it weren't for 3 or 4 important, but at the time, not now, but at the time, sort of forgotten papers. Those ideas were sort of, again, far-fetched at the time, and people didn't think much of them. And now it's driving a multi-billion-dollar industry. Another example is general relativity. A lot of people say, well, what good is general relativity? Okay, so maybe I can study black holes and things like that. People don't realize that they're actually using general relativity every day when they carry a phone around with them, because their phones usually syncs with the cell towers. It's also syncing with the GPS system. And the GPS system has to correct for general relativity, because if it doesn't, it's wrong by a large margin. I have my students do that calculation. It's a big mistake. Google Maps will be wrong. The time on your clock, on your phone, will be wrong. So those are sort of foundational, fundamental, deeply philosophical things that have made a huge difference in the way the world works.
Okay, so Ian, let's think about our annual countdown on this very podcast of the biggest stories in the foundations of physics. Regular listeners will know that at the end of every year, we take a look back and we think about the highlights of the year in physics and we rank the best items of the year. For those that haven't had a chance to listen yet, warning, there will be spoilers ahead. But coming top of our 2022 list were 2 results involving fusion experiments, which could make fusion more practically feasible as an energy source. And just missing out on that top spot was the DART mission, deflecting an asteroid in space, and also a lab experiment in which a well-established quantum effect, long known to be true for electromagnetic fields, called the Aharonov-Bohm effect, was demonstrated for gravitational fields for the first time. So if you haven't heard that edition of the countdown yet, you can go back and listen and find out why those items were such significant achievements. And I'll put links to that episode on the podcast page, qspace.fqxi.org/podcasts. That's the letter Q, followed by space, qspace.fqxi.org/podcasts. Ian, you wanted to talk a bit about how you go about making that list and what role the disruptiveness of the research plays into you making that choice.
So in thinking about our top 5 that we've been doing now for God knows how long, what I was thinking about when I read this paper was how many of these would qualify as disruptive in my head. I kind of pick them because they're big stories. They're important. They make a profound difference on the way we perceive things on a certain level. But are they really paradigm shifts? So in the words of Thomas Kuhn, who was a physicist and a philosopher, who I'm not a huge fan of Kuhn, but he sort of came up with this idea of paradigm shifts in science. How many of them will change the way we think about the world? I want to highlight one of our top 5 from this past year, and that is the gravitational Aharonov-Bohm effect. And we talked a little bit about this on the podcast, and I didn't make this number 1. And part of that is I had promised the fusion people that if they ever got their results that I would make them number 1, and I did. But the Aharonov-Bohm effect, a gravitational version of that, and I don't think people even realize how profoundly important this result is and will hopefully prove to be in the long term. And we talked about this a bit on the podcast, but it has to do with this idea that it makes you think differently about gravity. Because if you're a general relativist, gravity to you is not a force, it's just a bending of space-time. But the interesting thing about this is that the Aharonov-Bohm effect in a gravitational situation suggests that it has a lot more in common with your electromagnetic and weak and strong forces than we would originally think. Clearly, there is something funky going on. That's a deeply fundamental thing that could potentially change the way we think about gravity. And to look at our number 1, the fusion thing, and again, I do not want to minimize this, but there's nothing that physically would prevent human-made fusion from occurring. I mean, we know fusion occurs. It occurs in the sun. The fusion thing was more of a technological question. To some extent, it's a matter of how much money are you willing to throw at a problem.
I was just going to say that I feel like this is a sneaky way of you changing your number 1 from the countdown. And I feel very bad for the fusion people because, you know, they were so excited to have got the number 1 spot. But maybe this means that now we have FQxI merchandise. I don't know if you know that, Ian. We do have it. It's available on the website, FQxI.org. Maybe we need to send an FQxI hat to both the fusion team and to what was his name? I forgot his name, but the guy behind the gravitational Aharonov-Bohm effect. It will come back to me. Dave, I don't know if I should be asking you about the gravitational Aharonov-Bohm effect and or fusion.
You absolutely shouldn't be asking me about either of them. One in the case that I know very little about fusion, the other in the case that I know far too much about quantum gravity. In either case, you're going to get 5 seconds or 5 hours of discussion.
Let me ask, what are your thoughts on this paper? And also, what does it mean actually for something to be disruptive? What is the definition of that for you and I guess for this paper?
Right, so I can answer the easy part of that, which is how disruptive is defined in the paper, which, we can quibble over the exact definition. But within the paper, the idea is that a work is disruptive if once it comes out, it becomes cited much more than the papers that it cites. And therefore it's much more influential than the work that it was influenced by. So that's how these authors, broadly speaking, are defining something as being disruptive. Now, as I say, we can sort of quibble a little bit over whether that's fair. Perhaps some things will always get cited more. A paper couldn't be more disruptive than Newton's discovery of calculus, for example, for physics, because if you think back, calculus has influenced far more things. And yet you could say that the development of quantum mechanics or the solution of some differential equation systems can in themselves be very disruptive. But not sort of meaning to pick this apart, because I think this is vital work and this is something we really need to look at. What they do seem to be saying within this paper is that there are the same number, roughly, of disruptive works made every year, but the total amount of work is increasing. Therefore, the disruptive fraction keeps going down. So when it comes to Ian's list, you should still be able to find your top 5 every year, but you'll be picking them out of a much bigger haystack.
So I guess, Ian, is that necessarily a bad thing, actually? If you can still pick out a few disruptive things, does it matter that there are a whole bunch of other scientists making incremental advances? And why is that bad to make an incremental advance? Is it bad? I mean, people are doing good work and maybe big leaps come from lots and lots of very small steps building up on each other.
So I sort of take a different tack on this. I actually don't necessarily agree with their choice of disruptiveness. And I don't think that's what disruptiveness really is. But there's this general sense in, not just in the physics and science in general, but I think also in engineering and even in the general populace, that there's been less disruptiveness in the following sense. And this is the way I think about it. If you think back to when we were all children or our parents were children, we expected to have things like flying cars and stuff like that now, and we don't have that. A lot of the advancements that have been made in, say, the last 40 years have been to improve things like, so now you have a computer in your pocket, it's a phone, but is it a really novel idea that changes the way you think about the world? And I think disruptiveness, truly disruptive ideas, change the way you think about the world. I don't think that's necessarily captured in this paper. Now, what is captured in this paper is this idea of, there's a lot more incremental science that's happening. Is that a bad thing? No, that's not a bad thing at all. In fact, it's a necessary thing. As our understanding of science and technology improves, it's far more complex than we originally thought, right? So let me just give you an example. If you're going to major in physics, right, you have certain courses that you would take in college. But if you were to go back to Newton's time, half of those fields didn't exist then. It becomes clear that we can't make really big discoveries now without some of those incremental pieces, right? So when you look at the discovery of the Higgs boson and you look at the paper that actually was produced by that, there are like 1,000 people listed as authors on that paper, something like that. I mean, it's a crazy number of people that were required to do that. So if you look at the Higgs boson discovery, there were probably 100 papers that were papers related to the testing of the machines and the development of the actual Large Hadron Collider itself that all led to that. And so those are all incremental papers that led to that. And so I think that's part of what's going on here. But I also firmly believe that that's not what I think disruptiveness truly is. So I have a little quibble with their definition of disruptiveness.
Okay, so we have a quibble about what disruptiveness means, but even though we're sort of quibbling about what disruptiveness means, Ian has given us a sort of justification for why it's happening and why this is sort of natural in the way that science is done now, involving so many more people, so much more complex science. Do you agree? Is that why this shift is happening? And, can something be done about it, or does anything need to be done about it? Or do we just go, yeah, this is just the way things are now?
So first, yeah, I mean, it's certainly we can disagree about what the word disruptive means. But I think we agree that less disruptive science is happening. And to defend the authors just a little bit, they were trying to quantify disruptiveness, which is a very hard task, right? Actually being able to put a number on this and say this is a disruptive paper and this paper isn't disruptive. I mean, that's a very hard task, and I want to commend the authors for trying even to do that. I think it's a great service even to start the discussion on this. I do agree that incremental science is absolutely valuable. In fact, it's the backbone of rather a lot of science. But I disagree a little bit on why disruptive papers are less common. I think there are other root causes, and in fact, the strong impetus behind FQxI in some ways is to address those root causes. So the causes I'm talking about here are, for example, suppose I want to write a truly disruptive paper. I've got a brand new idea. I have this idea about, I don't know, quantum gravity that requires a completely different form of mathematics, a completely different way of thinking than anyone else has done before. I can't write that paper, very likely, in a couple of months. An idea, a truly disruptive idea, can sometimes take years or even decades to really coalesce and turn into some output. However, junior scientists, people getting into, for example, their first tenure track position, even all the way through the chain, are being pushed to publish and to publish rapidly. And so it's a lot easier for someone as a lower level scientist, lower level on the academic hierarchy, I should say, it's a lot easier to write incremental papers. It's a lot easier for me, for example, to write a lot of papers on an established theory, because I know I can write those quickly, and they're safe papers to write, they're safe papers to set my PhD student to write, for example. I wouldn't want to potentially send, a junior scientist down a dark alley, with no knowledge that they'll have something tangible at the end of it, because it would be bad for their career. But also, I'd be taking a very, very strong risk that I would have no employment at the end of it. And so there's a very strong discouragement away from doing this truly original, risky research. And that's something that FQxI really wants to address. We're all about revolution, not evolution. It's not saying there's anything wrong with evolution, but there's just not enough support for those willing to risk it all and follow a big idea.
So let me pick you up on that. And I know Ian wants to jump in here, but maybe let me focus this a little bit because, we're sort of patting ourselves on the back and saying, FQxI is all about big ideas and, whether it's paradigm shifts or whether we like that language or we don't like that language. We've been around now for 17 years. I mean, not necessarily with the three of us, but FQxI has been around for 17 years. And we provide funds to think about maybe disruptive things. We're trying to fund people to think about things they wouldn't otherwise be funded for. We're trying to, give people the opportunity not to have to write more and more papers about incremental advances. Is that enough? Is it just about pumping more money into it? Maybe not just by FQxI, but by other funding institutes? Is it just a question of money, or what is it? Or is there some kind of shift in something else? I don't know. Ian?
So I totally agree with Dave. I absolutely agree. I don't want to give the impression that I think that it's complexity that is the reason that we're not having breakthroughs. But Dave is absolutely 100% right. We also live in a world in which we don't value long-term thinking as much as we used to. And regarding the money issue, is it just a money issue? Part of the money issue is what it buys scientists is time. One of the things that I could use more of in a day is time to think about these things. The non-science and non-teaching related aspects of my job have, tripled, I would say, in the last 10 years. There's a lot more paperwork that has to be done. And those are the kinds of things that sort of also squelch big thinking.
So this isn't a million miles away from the topic of the essay competition. And that's sort of a coincidence because, this topic was decided on many, many months ago at FQxI. And yet at the same time, it's not a coincidence because it's just a very timely kind of idea, I guess, that people are trying to think about what's happening in science research. Dave, tell us a bit more about the essay contest. And I guess what I'm trying to get at is, what are we hoping to achieve here beyond sort of saying, wouldn't it be nice if science were, if there were more disruptive discoveries in science and engineering and technology? The end. What can actually be done about it?
One of the goals of this essay contest is for people to draw out their sort of scientific utopias. Because one of the key ways to advance, to take from state situation A to situation B, is you have to know what B is before you can draw a path that takes you from A to B. So if people have ideas that are better ways of communicating than, journals, I could talk at length about journals, but it's a method of communication that was ideal for Victorian gentlemen to tell you about their new findings, but in the era of the internet and mass collaboration and Wikipedia and so on, perhaps there are better ways to communicate than through scientific journals. And yet, as we talk about with career advancement and so on, publication in a journal is usually considered sort of the gold star for science being accepted. So are there better ways of doing that? And if you can think of better ways of doing that, perhaps you could help us design how we transition to that better way of being. So one of the things we'd love to see is, are there better ways of helping out people to communicate in science? Are there better institutions which could support scientists? And in fact, are there better systems which could produce and support scientists themselves? So are we playing with only a fraction of the team on the field in the way that people are chosen to become scientists? Should, for example, there be much more public participation? We know good ideas come from all over the place, so why is only a fraction of the population coming up with scientific ideas? So perhaps people who are entering the contest will have their own views and opinions on what's the best way to do science. And indeed, maybe your opinion is that the way we do things now is just great and you want to write a strong defense of that, and we'd be perfectly happy for that to come out too. One thing I do want to pick up on, though, is something that Ian said that I think is really important, and it's this freedom. The analogy with music, I think, is fantastic, because it's this freedom to play with an idea, to not even have a goal, to just simply have an idea and say, what if, and see where that takes you. So the most fun I've ever had doing research is when I've looked at something and gone, that's weird, what if? And then just started playing with the idea, playing with some equations with no goal in mind. I've never sort of sat down and thought, I'm going to calculate this effect out of it. I just want to see, if this were true, what would it do to the world? And the most fun you have is when you get into this sort of state of play. I think mathematically there's a really nice analogy here, and that's with the discovery of imaginary numbers. You learn in school that you can take square roots only of positive numbers. And then you just play the game of, -1 doesn't have a square root, but what if it did? Let's just play with that. Let's just see what this idea leads to. And you don't sit down with that thinking, this will make electromagnetism easier, this will explain quantum mechanics, this will have all these effects in how we do physics later on. You just sit down with that idea and you play with it for a while. And later the utility of the idea that you've been riffing off, I guess, comes to the forefront. But having that freedom, having that time just to say, I'm going to explore this sort of new world that's opened up with this idea, that, I think, is where the true disruption can come from.
So this actually reminds me, when both of you were speaking, it reminded me of a podcast that we recorded at a conference in Canada, I think in Banff. And Ian was part of that one as well. It was on creativity and science. And we had, various participants at the conference who were largely physicists. Not all of them were physicists, but people who had an interest in music. We had artists there. We had, science fiction writers there, and talking about sort of the common process between creating science and creating music, creating art. One thing that Ian just mentioned, and I think it did come up in that podcast, and it's sort of implicit in what you're saying there, Dave, is the importance of not worrying about being wrong. And what struck me as you were saying that was you both obviously have experienced this and have felt a certain sense of freedom and the ability to play around with ideas and think about things. But I'm also thinking about students in physics classes at school and at university level who are very scared of being wrong, who have been taught that when they're wrong, it means they're stupid or it means they don't understand. And so, it might just be the people that are immune to that feeling who can kind of, not be scared of that, who then go on and become physics professors and then talk to other physics professors about how wonderful this creative process is. But what about all those other people that get left behind through fear? Both of you are nodding your heads, and Dave has two hands up, whereas I think Ian only has one hand up. So I'll have to go to Dave first.
Thank you. That's absolutely central. In fact, part of the learning process I often go into with my students, because they come in with this idea that physics is about getting the right answer and, you have to get, the right number at the end of some calculation, and that proves you're good at something. The freedom to fail is one of the most important parts of learning physics. I always tell my students that I don't measure physics progress in terms of how many things I've done. I measure it in terms of how many balls of screwed up bits of paper of things that didn't work. I spend 99, maybe 99.9% of my time being wrong about things. But you've got to be wrong a lot in order to be able to find out what's right. You've got to explore a lot of paths that go nowhere in order to find the path that goes somewhere. And this freedom to fail is absolutely central to that. There's a classic sociological experiment. It's sort of a psychological, sociological experiment that is performed with people. And it was a brilliant indicator of the difference between a scientist and a non-scientist. And you can go and look this up on the internet. There's a brilliant site that does it somewhere. We can possibly give the links out. But the idea is you've got to identify a rule that some sequence has to obey, and the computer will give you some sequence, and you have to then enter sequences that obey this rule and then eventually guess the rule. The only way you can find the rule is by breaking it. The only way you can find the boundaries of, what is true is by finding out what's false. And so being wrong is absolutely key. And yeah, I think that we place too much emphasis on who can do this the fastest, who gets this idea first, who does the calculation most precisely at a young age. Whereas as a scientist, what you really want to be doing is developing the thought processes of, I try this and it doesn't work, so I try that and it doesn't work, and then I try another thing, and eventually you find the thing that works. So yeah, being wrong is being wrong is a huge part of who I am.
But sadly, Dave is ineligible from entering the FQxI essay contest, so he can't say anything more about that. But although it is anonymous, but we're going to have to just be really strict with him about not entering. But Ian, yeah, please go ahead.
So the first thing I want to say is that, both my kids are in the arts. My daughter actually had a project recently, last week, maybe it was even this week. She cited our podcast, the recording that you did in Banff, because she's taking a class on free play. It's a psychology class. So she was like, let's talk about free play and stuff, and how important it is to learn to fail and to learn to be self-sufficient in a sense. So she cited the podcast. I want to pick up on something that Dave said, is that, and I tell this to my students all the time, it's so important. You have to fail. And in fact, one of the things I tell my students is, if you get something right, how do you know you got it right for the right reason? meaning how do you know you actually understand it? So if you just calculate and you get a number and all I grade you on is the number, how do I know you didn't just pull that number out of your head? To give you an example, when I was in college, I took one course that had these exams that were all multiple choice, and it was an electronic circuits class. And I think back to that, and I think, boy, how did that really test my knowledge of circuits? It didn't. You have to fail, you have to fumble through because it's the process. The whole point of science isn't the final answer. The whole point of science is the process. It teaches you a process, a way of thinking. And I think that is so vitally important. And the only way you get that is from failing. And I also want to say, as someone who has been a veteran of 5 startup companies, that is also important in business too. And even in life, you have to fail. My first company failed. My second company failed. My third company failed. My 5th company is doing okay. And it's like W.H. Macy, the guy who founded Macy's, which is this huge store, right? It was like his 5th or 6th attempt to do something. He had failed at all of them. And, Babe Ruth is famous for hitting a huge number of home runs. He also struck out an insane number of times because, in order to do these big things, you have to think big. And when you think big, you also are inevitably going to fail big. And I think both of you hit on this. There's a fear. People fear failure. And that's something that somehow has to change.
I'm sorry, Ian. I was going to say maybe you should stop starting up companies, but it sounds like the 5th one was okay. So maybe it's all right. Okay. Last question then. What is your favorite, seeing as we're talking about disruptive ideas, I guess in recent times, what is your most favorite disruptive idea, disruptive result? And you're not allowed to say Einstein or quantum theory, but something else. Doesn't even have to particularly be about physics. Dave?
Quite possibly, I'd say even something like Wikipedia. I'd even say some idea about the internet or some mass sociological experiment that is the internet is a vastly disruptive idea on a sociological scale. Now, whether or not it's a force for good is a wide open question there, but certainly the idea has been very disruptive.
Yeah, I like that one. Okay. Ian?
That's a really good example. I mean, the internet, in terms of changing humanity, there's not a whole lot could come close to that in recent times. So that being said, funny enough, even though I'm a sort of a big picture kind of guy, I was thinking in sort of smaller terms. And, on the science level, the Aronoff-Bohm effect thing for gravity just strikes me as, wow, that's a really profoundly different way of looking. Like, it really changes the goalposts to me in the sense of it says something very fundamental about gravity that we didn't know things. Of course, I would also mention, and this is definitely not a force for good, and it's more of a gradual effect, but of course, climate change, human-centered climate change is going to have a massive, massive effect. It's already having a massive effect on humanity. And basically, if you were to point to one thing about that, it's the Industrial Revolution. The Industrial Revolution, certainly changed humanity in a lot of positive ways, but it also may be the end of us.
Right, and on that terrifying note, we will draw an end to this discussion. If you want to go back and listen to us talking in much more depth about the gravitational Aronoff-Bohm effect, you can find out more by heading over to the podcast page, the new podcast page, qspace.fqxi.org/podcasts. And if you get lost, just go to fqxi.org and hit the QSpace button on the top right. Also, once you're on QSpace, if you head over to the competitions button, you will see that we are now taking entries for this year's essay competition, asking how science could be different. The prize fund is a whopping $40,000, and we're interested in fiction and non-fiction, and entries from scientists and non-scientists, as Dave mentioned. Once those entries start coming in, We will be posting them to the site where people can read all the eligible entries and discuss them in our forums and vote for their favourites. So please do head over there and join the debate. I'll also, of course, be linking to the paper on scientific disruption in Nature and to the Science and Creativity podcast that we mentioned too. That's all we have time for, so I will say thank you and goodbye to Ian and Dave. Say goodbye, Ian and Dave.
Goodbye, Ian and Dave.
Bye, Ian and Dave.
You knew that was coming.
Goodness sake, children. And thank you for listening. You can reach me on Twitter at FQxI, where Ian is at QuantumMoxie, and we're both also on Mastodon at FQxI at sciencemastodon.com and at QuantumMoxie at sciencemastodon.com. FQxI is also on LinkedIn and YouTube as at FQxI. And if you subscribe to our YouTube channel, you will have another way of listening to the podcast, as well as being able to watch a new series of films we are in the midst of releasing, featuring some of our scientists around the world in their labs. We are at FQxI Physics on Instagram, Facebook and TikTok. Oh yes, you can see Ian on TikTok, and Pinterest. To play us out, here's a trailer for the Great Mysteries of Physics series. In the meantime, I've been Zeeya Merali.
It's much harder to tune a radio than to tune a universe.
There is nothing new to discover in physics now. That was the bold claim made by the British physicist Lord Kelvin in 1900. He was wrong. It's increasingly clear that there are problems that physics, at least as we know it, cannot solve. Perhaps we just need more data, or perhaps we need a whole new theory of reality. Welcome to Great Mysteries of Physics, a new podcast from The Conversation supported by FQxI, the Foundational Questions Institute, and presented by me, Miriam Frankel. This podcast series will take you on a mind-blowing journey from the smallest particle to the very boundaries of existence. We'll reveal the greatest mysteries facing physics today and investigate the radical possible solutions. We'll explore topics like the multiverse.
So I usually say 2 cheers for the multiverse, because I think it's better than just saying God did it.
Investigate fundamental constants and how they make life possible.
I don't think our universe is fully optimized to be the best it could be.
And we'll dive deep into the hidden nature of reality.
But there are other ways the laws of nature could be. They could be more like the rules of a game of Sudoku.
Which can give even the brightest minds a bit of a headache.
So this was described by Stephen Hawking as the greatest failure of theoretical physics in history.
While taking stock of different theories and opinions in the physics world, because not everyone agrees with one another.
So I actually think that physicists are a little bit confused with what they even mean when they talk about evidence.
We'll be speaking to incredible physicists, including Sean Carroll, Sabine Hossenfelder, Paul Davis, Emily Adlam, and Fred Adams, and many, many more. And we won't shy away from the existential questions such as the baffling role of consciousness in physics.
The ability to make choices on the basis of information is crucially important and real. So just like I think that the table is real even though it's made of atoms, I think free will is real as long as we're talking at the level of human beings.
As we examine the research out there, we'll hear from those who are challenging our assumptions about what we think we know about our home galaxy.
So the problem is not that we do have mysteries. What worries me more is that we don't seem to make any progress solving those mysteries.
In 6 episodes, I'll be there to take you on a journey through the cosmos to decipher the great mysteries of physics. Subscribe to our podcast, Great Mysteries of Physics, coming soon.